Welcome to This Explainer. Okay, today we are diving headfirst into a literal high-stakes crisis in cosmology, a crisis that honestly threatens our entire understanding of the universe. You see, for decades, the standard model of cosmology has been our guiding light, right? It's the reliable map that explains exactly how the universe works. But lately, the numbers just aren't adding up at all. And it's pointing to a massive, mind-bending mystery right in our own cosmic backyard.
So let's jump right into the big question. Is our universe broken? I know, it sounds super dramatic, but the fundamental laws of nature genuinely seem to be failing us right now. Why? Because the universe's expansion rate literally isn't matching up depending on where we look. And we're not talking about some tiny rounding error here. It's a statistically significant mismatch that has thrown the entire world of astrophysics into a complete crisis. Basically, something is fundamentally wrong with how we see the cosmos.
We essentially have two sets of completely conflicting clues. On one side, we have our local measurements, stuff we measure using supernovae and Cepheid variable stars. And these show a surprisingly fast expansion rate for the universe. On the flip side, we have our early universe predictions. Think of it kind of like figuring out the size of a musical instrument purely by listening to its pitch. We know the size and the expansion rate of the early universe from the pitch of the cosmic microwave background fluctuations. But here's the kicker. This early universe data predicts a much slower expansion rate.
Take a look at this. Notice the glaring gap between that horizontal orange band, which represents our fast local data, and the tiny gray ellipse with the white star in it. That gray ellipse is the slow, early universe prediction from the cosmic microwave background. This gap, this incredibly stubborn disagreement, that is the famous Hubble tension. It's essentially the ultimate cosmic whodunit, and it's forcing us to ask, do we literally need to rewrite the laws of physics to make these two completely different measurements agree?
Section 1. The Local Void Solution, Living in a Cosmic Pothole. Well, hold on. Before we throw out the physics textbooks, let's look at our prime suspect. And this suspect reveals a pretty shocking twist about our actual place in the universe. The solution to this massive crisis might simply be that we aren't actually observing an average normal patch of the universe. Instead, it looks like we are looking out from inside a giant, underdense cosmic pothole. We call this the KBC void, named after Keenan, Barker, and Cowie. It is a massive bubble of space, roughly 300 megaparsecs wide, that entirely encompasses our Milky Way. So we aren't in a typical cosmic neighborhood at all. We are actually sitting in the cosmic middle of nowhere. Okay, let's break down this logical chain of events to see exactly how a void tricks our measurements into seeing a much faster expansion rate. Step 1. The severe lack of mass inside our bubble creates an outward gravitational pull toward the denser, heavier edges of the void outside. Step 2. This outward pull generates what we call peculiar velocities. Basically, local galaxies are physically rushing outward, which artificially inflates the local expansion rate we're observing. And step 3, gravitational redshift further alters the light we see, because our observations literally have to climb out of this gravitational hill. And that brings us to an absolutely crucial number, 11%. Based on the observed underdensity of the KBC void, physicists have calculated that these outward velocities and gravitational shifts should inflate our local expansion measurements by roughly 11%. And honestly, what is absolutely brilliant about this is that an 11% inflation perfectly bridges the gap in the Hubble tension. The universe itself isn't expanding too fast. Our local bubble is just expanding faster than the rest of the cosmos. Moving on to Section 2, the Bayo distance anomaly, the second clue. Now, you might be wondering, if we really are living in a giant void, shouldn't there be other anomalies hiding in our local data? Well, yes. Take baryon acoustic oscillations, or Bayo. These act as our standard cosmic rulers. And recently, a massive anomaly popped up in this data. At low redshifts, meaning stuff that's closer to us, the distances to galaxies appear anomalously smaller than standard model predictions. But here is exactly where the void theory shines. Because our local expansion rate is artificially inflated by the void we're sitting in, the distances to a given redshift will naturally appear artificially shorter than they actually are. And this brilliantly illustrates that exact phenomenon. See the flat, straight gray line across the top? That is the standard model prediction. But those colorful dots, which represent actual BAO data collected over the last 20 years, are visibly dipping down below it at the lower redshifts. Now check out the solid colored lines. Those are the void model predictions. And get this, they were mapped out years before some of this newer data even existed. The solid void model lines match the dipping data points absolutely perfectly. It is literally an elegant fit. If you compare the cosmic expansion history across the different models, it reveals something really fascinating. Notice how the colored void solution curves are acting purely locally over on the left side, right? They're neatly tying off both the Hubble and the BAO anomalies. But as we look further out in space and time, moving to the right, the void models converge right back with the thick black line, which is the standard CMB consistent expansion rate in the deeper universe. So it fixes our local problems without breaking the physics of the deep universe.
Section 3. Testing the void hypothesis, proving the cosmic bubble.
Look, resolving this crisis without having to rewrite the fundamental laws of physics is a massive relief. But obviously, science demands hard proof. To figure this out once and for all, cosmologists are preparing some genuinely futuristic ways to test this theory and map out our void. We're looking at tools like fast radio bursts, or FRBs, to measure the missing matter directly, the redshift drift experiment to track cosmic changes over decades, and the kinematic Sanyayev-Zeldovich effect, which measures the actual physical velocities of galaxy clusters. Let's zoom in on that first one, because fast radio bursts are a genius tool for this. As the theory proposes, FRBs should give a higher estimate of H0 than other techniques based on standard candles, rulers, or clocks. Why is that? Well, FRBs indirectly measure the density of electrons in space by looking at the delay of the radio wave's arrival time. If we are truly in an underdense void, that missing matter will show up directly as a smaller delay in the FRB signals. It's a direct, physical probe of our cosmic emptiness. And thinking long-term, we have experiments like the forecasted redshift drift. Instead of just taking a static snapshot of the universe on our past light cone, this experiment will let us actually watch the gravitational redshift and peculiar velocities change in real time over a decade or more. Now, this signal is incredibly tiny. We are literally talking millimeters per second over 10 years. But next-generation instruments that are currently under construction will allow us to essentially watch our local void expand around us. How cool is that? So, what should we take away from all this? Honestly, it leaves us with this thrilling, kind of humbling final realization. What if the fundamental laws of the universe aren't actually broken at all? What if we're just living in the cosmic middle of nowhere? The physics of the cosmos might be perfectly intact, but our place within it is far less average than we ever dared to imagine. It's a great reminder that sometimes the biggest mysteries in the universe can be solved just by understanding the very ground we're standing on. Thanks for joining me on this explainer, and definitely stay curious.